Next chapter, magnetic effect of an electric current. Let's talk about electromagnetism. Now, scientists for very many years knew there was some link between magnetism and electricity, but they just couldn't find it. There were a lot of clues that pointed in that direction. Both magnets and electric charges produce fields around them. Magnets produce magnetic fields, and charges produce electric fields around them. Again, like poles of magnets repel, while unlike poles attract each other. And in the same way, like charges repel, while unlike charges attract one another. But there was a small disparity. They knew that magnetic fields are produced and could be detected using a compass. If you move a compass around a magnet, you can see that it is lining with that magnetic field. And so what they wondered was, maybe if we take a compass and move it around a charged object, there will be some deflections, but there simply wasn't any. And so it didn't seem like charges were producing any kind of magnetic fields. But in 1820, a brilliant Danish physicist, Professor Hans Christian Ørsted, discovered that a current-carrying conductor generates a magnetic field around itself. In other words, moving charges produced magnetic fields. Ørsted placed a compass below a conductor in an electric circuit. When no current was flowing in the circuit, the compass needle pointed in the usual north-south direction. But when current was allowed to flow, the compass needle deflected. When the current direction was reversed, the compass deflected in the opposite direction. Again, he placed the compass above the conductor and allowed current to flow. Deflections occurred but were reversed. It therefore means stationary charges only produce electric fields, but moving charges produce both electric and magnetic fields around them. Ørsted also observed that when the magnitude of the current flowing in the conductor was increased, the deflection of the compass needle also increased. When the compass was moved closer to the conductor for the same amount of current, the deflection increased. Let's talk about the magnetic field pattern of a straight conductor. Now, the magnetic field pattern of a straight conductor could be found by placing a cardboard in a horizontal position with the conductor passing through a hole in the center such that the wire is perpendicular to the plane of the cardboard. Some iron filings are sprinkled on the cardboard. When current is passed through the conductor, the iron filings arrange themselves in concentric circles with their center coinciding with the center of the conductor. This proves that the conductor produces a magnetic field around it when current passes through. It is also found that the alignment of a magnetic needle is tangential to an imaginary circle with a straight current-carrying conductor at the center, and the plane of the imaginary circle is perpendicular to the conductor. The direction of the magnetic field produced by a straight conductor can be found using certain rules. The right-hand grip rule, the Maxwell's corkscrew rule, and the Ampere's swimming rule. The right-hand grip rule states that if a straight conductor is grasped in the palm of a right hand with the thumb pointing in the direction of current flow, then the direction of the curled fingers point in the direction of the magnetic field. Maxwell's corkscrew rule states that if the direction of a linear motion of a corkscrew represents the direction of the current through the conductor, Then the direction of rotation of the screw gives the direction of the magnetic field. And Ampere's swimming rule states that if a man swims along a current-carrying conductor such that his face is always towards the magnetic needle, with current entering his feet and leaving his head, then the north pole of the compass needle is always deflected towards his left hand. Next, magnetic field pattern of a circular current-carrying loop. We have a drawing board and fix a white paper sheet over it. We make 2 holes A and B and pass a thick copper coil through it. The 2 ends of the copper loop are connected to a source of current. The circuit is closed and the magnetic field plotted using a compass needle. The magnetic lines of force around A are in the anti-clockwise direction, and around B, the lines are in a clockwise direction. The direction of magnetic field for a loop can also be determined using the right-hand grip rule for a loop. It states, if the direction of the circular current coincides with the direction of the curled fingers, then the thumb points in the direction of the magnetic field. Next is the magnetic field pattern of a solenoid carrying current. Now, the magnetic field around a wire carrying current can be intensified by winding the wire into a long cylindrical coil with many connected loops, otherwise called a solenoid. Using a number of compasses or iron filings, it can be shown that the field set up by a solenoid is similar to that of a permanent magnet. And therefore, a solenoid carrying current behaves like a bar magnet. It is referred to as an electromagnet since its magnetism arises from the flow of electric current. The clockwise and anti-clockwise rule can be used to predict polarities of the electromagnet formed. The rule states that if the direction of the current in the coil as observed from one end is clockwise, this end is the south pole. And if the current is anti-clockwise, the end becomes the north pole. Next, let's talk about the factors affecting the strength of an electromagnet. In this setup, we have created an electromagnet by winding a current-carrying conductor around a soft iron bar. The rheostat is used to regulate the amount of current flowing through the circuit. When magnetized, the iron bar will attract the pins in the petri dish. The number of pins attracted will be an indicator of the strength of the electromagnet. The ammeter measures the amount of current flowing. We close the circuit and vary the current, each time recording the number of pins picked in the table here. From this table, it is clear that as current increased, more pins were picked. This indicates that increasing current increases the strength of the electromagnet. Now let us investigate the effect of the number of turns of the solenoid. Again, the number of pins picked will indicate the strength of the electromagnet. We switch on the current and record the number of pins picked. We will notice that as the number of turns increases, the number of pins attracted increases as well. This shows that the strength of an electromagnet increases with increasing number of turns. How about the core material of the magnet? We can investigate this by using different materials as the core of the electromagnet for the same amount of current and number of turns. We shall still observe the number of pins picked by the core material upon magnetization. And from the observations, we can conclude that the strength of an electromagnet also depends on the core material used. It is most powerful when a soft iron core is used. This helps to concentrate the magnetic field lines that pass through it and hence producing a stronger electromagnet. And finally, does the shape of the core affect the strength of an electromagnet? Now, a solenoid of 20 turns is wound on a straight soft iron core. Another similar solenoid is wound on a U-shaped soft iron core. When the same amount of current flows in the solenoids, it is found that the U-shaped electromagnet attracts more pins. The U-shaped electromagnet has two opposite poles adjacent to each other. The magnetic field lines are concentrated in the space between the two poles, resulting in a stronger magnetic field. Next, force on a current carrying conductor in a magnetic field. And so, when a current flows in a conductor, it exerts a force on a magnet placed in its vicinity. Is it possible for the process to be reversed? A French scientist, Henri-Marie Ampere, suggested that a magnet must also exert an equal but opposite force on a current carrying conductor near it. Consider a short aluminum rod AB. We suspend it on a stand with two conductors as shown here. Place a strong horseshoe magnet in such a way that the rod lies between the two poles with the magnetic field directed upwards. Connect the rod to a battery with a switch. When the switch is turned on and current allowed to flow through the aluminum rod, it is deflected towards the left. This indicates that a force is exerted on the current carrying aluminum rod when placed in the magnetic field. Now we reverse the current. The deflection occurs, but in the opposite side, suggesting that the direction of the force is reversed when the direction of current is reversed. And if we reverse the magnetic poles, deflections occur, but they are reversed. In short, the direction of force on the conductor depends on the direction of current and direction of the magnetic field. Experiments have shown that the magnitude of the force is greatest when the direction of current is at right angle to the direction of the magnetic field. We use the Fleming's left-hand rule to determine the direction of the force on the conductor. According to this rule, if you stretch your thumb, forefinger and the middle finger of your left hand in such a way that they are mutually perpendicular, with your forefinger pointing in the direction of the magnetic field, your middle finger pointing in the direction of current, then your thumb points in the direction of the force acting on the conductor. This is a diagram of the side arrangement. First of all, conventionally, when we indicate current moving away from us, we use a cross in a circle. And when coming towards us, we use a dot in a circle. So in this case, the brown circle represents the wire with current coming towards us. The magnetic field around the wire due to current is clockwise, looking in the direction of current, but to us, it is anti-clockwise. The magnetic field of the permanent magnet runs from north to south, and the two fields interact. On the left, they both flow in the same direction and reinforce one another. And on the right, they run in the opposite directions and tend to cancel out. The magnets are huge and cannot therefore move. The wire is light and gets flipped out of the magnetic field. The thrust takes it away from the strong magnetic field and towards the weak field, as the system tries to reduce the concentration of the magnetic flux on the left. Next, force on a current carrying coil in a magnetic field. Now, when a current carrying coil is placed in a magnetic field, the catapult force acting on it can also be determined using the Fleming's left-hand rule. On the left side, the force pushes the coil upwards, while on the right, it is pushed downwards. These two equal and opposite forces produce a turning effect which causes the coil to rotate in a clockwise direction. If the direction of the current is reversed, the direction of rotation will also be reversed. The forces are produced by combination of the magnetic field due to the coil and due to that of the permanent magnet. This diagram shows the side view of the combined magnetic field. The two sides of the coil produce circular magnetic fields in opposite directions. The two forces which are in opposite directions make a couple which produce a turning effect, and the coil rotates in the clockwise direction. Next, force on a charged particle moving in a magnetic field. Now, we said a moving charge produces a magnetic field around it in addition to the electric field. When such a charge moves through a magnetic field, the two magnetic fields interact, causing the charge to experience some force and thus change its direction. The direction of the force can be determined using the Fleming's left-hand rule. Now, consider a charge moving close to a current-carrying conductor. We know that such a charge has a magnetic field around it. The current-carrying conductor also has a magnetic field around it. These two fields interact, causing the charge Q to deviate from its path. If the charge Q is projected from point P in the direction of the current in the wire, it gets deflected towards the wire if the charge is positive, and away from the wire if it is negative. If the charge moves in the opposite direction to that of the current in the wire, it gets deflected away from the wire if it is positive, and towards the wire if it is negative. Forces between parallel conductors. When two conductors have current flowing in the same direction, the magnetic field between them is created in the opposite direction. The north and south poles so created attract each other, and the two conductors are drawn towards each other. When current is in the opposite direction, we find the direction of the magnetic field for each wire as per the Fleming's left-hand rule. Both wires create the same magnetic field between them and hence repel each other. Finally, we talk about the applications of electromagnets. And we start with the electric bells. An electric bell consists of two terminals, T1 and T2, connected to a source of current through a push-button switch. When the button is pressed down, current flows through the solenoid and then to the contact screw, all the way to terminal 2 to complete a circuit loop. As the current flows, the solenoid becomes an electromagnet and pulls a soft iron armature strongly towards itself. The spring connecting the stud S and the armature gets under tension. The hammer strikes the gong, producing the sound. Meanwhile, the circuit breaks at the contact point. This causes demagnetization of the electromagnet and thus cannot hold the armature. The spring under tension pulls the armature away from the solenoid. This re-establishes the contact and the circuit is once again complete. The solenoid is magnetized, pulls the armature, the hammer hits the gong, and the current is broken again. This process continues on, and the bell makes a continuous sound as long as the button is pressed down. Next is the magnetic relay. A relay is an electromagnetic switch used in applications to turn on and off a circuit by low power signal, or where circuits must be controlled by one signal. Its main parts include an electromagnet, a movable armature, switch point contacts, and a spring. There are two circuits: control circuit and the load circuit. When the control switch is turned on, current flows and activates the electromagnet, which attracts the armature, and thus the load circuit is closed as well. And so in a relay, one circuit is used to control another circuit without any direct electrical connections between them. The electric motor. Now, a motor is a device that converts electrical energy into mechanical energy. The working is based on the principle that when a current-carrying conductor is placed in a magnetic field, it experiences a force. It consists of a horseshoe type of magnet and an armature coil ABCD, which is rectangular in shape. The coil is placed between the two poles of the magnet in such a way that the arms A, B, and CD are perpendicular to the direction of the magnetic field. The ends of the coil are connected to the two halves S1 and S2 of a split ring. This is called a split ring commutator. It is free to rotate along with the coil. Its role is to reverse the current direction after every half rotation. The inner sides of these halves are insulated and attached to an axle. A pair of brushes B1 and B2 touch the split ring S1 and S2 respectively. The current in the coil is supplied through these two brushes. A battery and two connecting wires are connected to the brushes. When the coil rotates, the split rings rotate, but the brushes do not. Current enters from the battery through brush B1 and flows back to the battery through brush B2. Notice that the current in arm AB flows from A to B, and in arm CD, it flows in the opposite direction, that is C to D. Applying Fleming's left-hand rule, we find that the force acting on arm AB pushes it downwards, while the force acting on arm CD pushes it upwards. These two forces turn the coil anti-clockwise. After half a rotation, the split ring S1 is in contact with brush B2 and S2 is in contact with brush B1. Therefore, current in the coil gets reversed and flows in the path DCBA. This current reversal also reverses the direction of the force acting on the two arms. Applying Fleming's left-hand rule again, we see that the arm AB, which was earlier pushed downwards, is now pushed upwards. And arm CD, previously pushed upwards, is now pushed downwards. The reversing of current is repeated at each half rotation, giving rise to a continuous rotation of the coil.